Rectangular waveguide. From invention to application. Rectangular waveguides play a foundational role in modern high-frequency electronics. In this video, we explore their origins, design principles, mathematical theory, and real-world applications. Invention of the waveguide. The concept of guiding electromagnetic waves through a hollow structure emerged in the early 20th century. In 1897, Lord Rayleigh theorized about wave transmission in hollow pipes, but it wasn't until the 1930s that George C. Southworth at Bell Labs experimentally demonstrated wave propagation in a rectangular metal tube. This invention laid the foundation for radar and microwave communication during World War II. This was a critical step in high-frequency technology, replacing lossy alternatives like open wire or coaxial systems. Why waveguides were needed? As frequencies increased in early electronics, traditional transmission lines like coaxial cables began to fail, with higher losses, overheating, and interference. Engineers needed a solution that could contain, direct, and sustain microwave energy with minimal loss. Waveguides offered this, a metal structure where electromagnetic waves could bounce and propagate efficiently. They also offered better EMI shielding and higher power handling, which became vital in defense and satellite systems. Types of waveguides. Waveguides come in several shapes: rectangular, circular, elliptical, even ridged. Among these, the rectangular waveguide became the most widely used, thanks to its predictable electromagnetic behavior and easier fabrication. Standardized waveguides like WR90 and WR75 serve specific frequency bands, improving interoperability between systems. Structure of the rectangular waveguide. A rectangular waveguide is a hollow metal tube, often made of copper or aluminum. It has a length much greater than its cross-section. The longer internal side is labeled A, the shorter B. No energy is lost through the metal walls, which are treated as perfect electric conductors in theory. In practice, the metal has some loss, but high conductivity minimizes this. Precision machining improves performance. How waveguides work. Electromagnetic waves inside the waveguide bounce off the conducting walls and propagate down the length. These fields form standing patterns in the cross-section while the overall wave energy moves forward. This is fundamentally different from energy conduction in a wire, which involves moving charges. The fields are solutions to Maxwell's equations constrained by boundary conditions, making them stable and efficient. No transverse electric modes. Because waveguides are hollow and have no central conductor, they cannot support transverse electromagnetic waves. Instead, they support transverse electric modes. No electric field in the direction of travel. Transverse magnetic modes. No magnetic field in the direction of travel. This is a key distinction from coaxial lines, which support only the transverse electromagnetic mode. Mode numbers and cutoff frequency. Each mode has a unique configuration defined by integers m and n, the number of half-wavelength variations in width and height. For example, transverse electric 1, 0, 1 variation in width, none in height, the dominant mode. The cutoff frequency is given by c divided by 2a, where c is the speed of light and a is the waveguide width. Below this frequency, energy is attenuated and does not propagate. Propagation characteristics. Below cutoff, signals decay, they don't propagate. Above cutoff, waves propagate with phase velocity greater than c, but with group velocity less than c. This doesn't violate relativity because no signal or energy travels faster than light. field patterns. In transverse electric 1-0 mode, the electric field peaks in the center and is zero at the walls. The magnetic field loops around the electric field lines. These patterns are key for designing junctions, filters, and couplers. Wave impedance and power handling. The wave impedance depends on frequency and mode type, not constant like in coaxial lines. Waveguides also handle higher power because there's no dielectric to heat up and no central conductor to arc or burn. Impedance for transverse electric mode is given by Z is equal to eta divided by root over 1 minus square of Fc divided by square of F, where eta is 377 ohms in air. Materials and fabrication. Most waveguides are made from copper for low loss, aluminum for weight saving, sometimes silver plated for ultra low resistance. Precision machining ensures clean interior surfaces to reduce reflections. In some cases, flexible waveguides are used where routing requires bending. Applications. Rectangular waveguides are used in radar antennas, satellite ground stations, microwave ovens, medical imaging like MRI coil systems, aerospace and defense systems. Their role in modern wireless communication remains vital. They are also used in particle accelerators and high-frequency test equipment. Transition elements. To connect waveguides to coaxial or microstrip lines, engineers use coax-to-waveguide adapters, mode converters, flanges, and flexible waveguide sections. These ensure efficient energy transfer between different transmission technologies. Matching sections minimize reflection and ensure smooth power transition. Challenges and design considerations. Designing a waveguide system means accounting for operating frequency, reflection coefficients VSWR, bend ready, thermal expansion, moisture ingress, which can detune the guide. Good design balances all these to ensure efficient signal flow. Environmental sealing and pressurization are sometimes required in satellite and defense systems. Modern trends and miniaturization. Today, engineers use micro-machined waveguides for millimeter wave and terahertz systems. There's also ongoing research into metamaterial-based waveguides, integrated photonics, blending optics, and microwave theory. These technologies aim to combine the high performance of waveguides with the flexibility of modern integrated circuits. Guide wavelength. Inside a waveguide, the wavelength lambda g differs from free space wavelength. It increases near the cutoff and is given by lambda g is equal to lambda divided by root over 1 minus fc square divided by f square. This must be considered in the physical layout of components like cavities and filters. Real versus ideal behavior. Although theory assumes perfect conductors and no losses, in practice, finite conductivity causes attenuation. Losses are proportional to surface resistance, minimized by polishing and plating interior walls. This makes material and finish selection critical in high-power systems. Recap and summary. Let us have a small recap. Waveguides were born from early 20th century physics. Rectangular waveguides are still a gold standard in RF systems. They offer low-loss, high-power performance for critical applications. Understanding their theory from TE10 mode to field patterns helps engineers design better, faster systems. Thanks for watching. If this guide helped you out, don't forget to subscribe for more easy tutorials. Keep exploring and have fun learning.